well, actually, 5 is split into 2 different areas. But I want to go over them because there were questions on each of them. So I'm going to start with assignment number 3. Okay, most of this assignment was on the confidence intervals, and I think probably the most involved one is probably the last one. So let me just take a look at that. I know there was at least one person had a question on it. Let's see. Researchers, nutrients was calcium. Let me see if I have this one. Let's do this question here, which is question 10. Researchers examined estimated dietary and technical ingredients. One of the nutrients was calcium, milligrams for adults 60-year-old. Found the mean intake was 621 milligrams, with a standard deviation of 254 milligrams. Using these values for the mean and standard deviation, sigma, for the United States population, compute the probability that a single randomly chosen adult over 60 years old will have a daily calcium intake over 900 milligrams. Well, first of all, number one, they gave us the mean and the standard deviation for the entire population, both the mean and the standard deviation. So we actually know all about this population. Okay, presumably either such a big study that we're going to assume that's the true mean, the probability that in order to calculate the probability that a single randomly chosen adult over 60 years old would have a calcium intake of over 900 milligrams, well, this is a normal distribution problem. I'm just going to mention it quickly because you probably won't be getting something like this on the exam. But I just want to make sure we're clear on the difference between when we're dealing with a population mean and standard deviation and when we're dealing with a sample mean and standard deviation. Okay, let me just get my graphics tablet working. So in this example, the mean was 721 with standard deviation of 254. Here's our normal distribution. This is the entire population. 721 is the mean, mu, and standard deviation is 254. And we were wondering what was the probability of taking a single person from this population and the probability that would have a calcium level over greater than 600 milligrams. Okay, so I just want to check to make sure that it's 600. Okay, good. So, was it over or under? Over 900 milligrams. Excuse me. So 900 is going to be on this side. Okay, so we're interested in knowing what this proportion of the population represents. What's the probability that we would pick someone out from this area of the normal distribution rather than the area below 900? Okay, so whole area represents 100% of the population. So yeah, good. Z is equal to, what's it equal to? It's equal to X, the value that we're interested in, not X bar, just X. X minus mu over the standard deviation. Exactly right. 721 minus, so it's going to be 900 minus 721 over 254. So it's going to be equal to 0.7. Now that is the number of standard deviations away from the mean. That's what Z represents. The T represents that as well, but it represents it when we have a sample and we're looking at the way samples behave. And samples can, because we're not sure of the true standard deviation, samples are a little less definite, so they tend to be wider. So the T-score might be different for a T distribution if we were looking at repeated samples. In this case, we're just looking at the population standard deviation. So this area that we want to the left here, we can find from the Z table or from Excel. I'll do it both ways just so we know. Let's see if I can come up with it. Okay, so a z-score of 0.7, positive 0.7, 0.70. I'm going to take your word for it. Okay, a z-score of a positive 0.70 comes out to be about 76%, 0.758, roughly 76. So 76% of this distribution is below that level of z. So if I go back here, this represents 76% of the distribution. And so that means that we're left with 24% of the distribution. That's above an intake of 900 milligrams per whatever, per month or day or whatever. Okay, so I'm going to move on to the last question, which I think is actually a real, actually does involve, or maybe it doesn't. Actually, no, I think these are all populations. So I'm going to move on to 4 instead. Yeah, well, let me just check 3 again. I don't think it's a confidence interval there either. You'd probably say, yep, doesn't involve a distribution. So probably not going to see much of that on the test tomorrow, but just so we understand that back then, before, for exam 1, we were dealing with population distributions. Now we're dealing with sample distributions. So I'm going to open number 4. Okay, and let's take a look at this one. Okay. Oh, this one doesn't seem to have taken. Oh, no, wait a second. I got it here. Okay. Oh, this is my zombie problems. Okay. So let's see what we have here. We want to find a 95% confidence interval for the mean cholesterol for all zombies. So what do we know? We've taken a random sample of 25 zombies, and we found that the mean of the sample was 151.4, and the standard deviation for the population, sigma for zombies, is assumed to be the same for all living humans, which is 38. So we're in this case, we're taking a situation where we've taken a sample, size 25. We find that the mean is 151.4, and we're going to assume that we know the population standard deviation. A little bit different than we would normally see in a real life, but we're going to work with this for the moment, just so that we can see how we would handle this differently if we knew what the population standard deviation was. I'm going to move this over here so I can see it. So in this case, the mean of the sample, x bar, is equal to 151.4. The standard deviation of the population is equal to 38. And the sample size was equal to 25. Okay, so now we want to see what the likelihood, what range of values that we would expect to get if we took repeated samples of size 25 from the population that this came from. And if we did, we would expect that with a sample size of 25, we would expect a certain kind of distribution, a certain width for that, all those different outcomes to be. Now, we don't know the true mean. So we can't start from the true mean and say, oh, we're going to take the true mean and go this much less and this much more, the margin of error less, margin of error more. We can only work with what we have, which is the actual mean of the sample that we took. Okay, so we're going to actually calculate our confidence interval by saying, well, it's going to be equal to x bar plus or minus some margin of error that we're willing to accept. And we're going to say that we're 95% sure that the true mean is within that range of numbers, which is going to be the margin of error subtracted from x bar and the margin of error added to x bar. So let's give that a try. So we know the margin of error is calculated this way. Well, first we're going to put x bar plus or minus the z-score times the z-score, which represents a 5% chance of being wrong. Alpha is equal to 5%, times the standard error. Now, the standard error is not the standard deviation in the population, because that's the distribution, that's the width of all of the individual people. We're interested in the width of the distribution of means for sample size 25, which is going to be narrower. So the way we calculate that, we say standard error is equal to sigma over the square root of the sample size, which is 25. So that's going to be 38 divided by 5, which is going to be 7.6, I guess, right? I think so. So 7.6, okay, which is our standard error. Now our z-score is the number of standard deviations we would have to go to the right and to the left to capture 95% of the possible outcomes that we might have for a sample size of 25, means for a sample size of 25. So I'm going to substitute for that z. I'm going to substitute 1.96. Okay, so I use 1.96, which is the z-score for a 95% confidence interval or 5% alpha. I'm going to use that because I know the population standard deviation. If I didn't know the population standard deviation and only know the standard deviation for the sample, well, then I would use the equivalent t-score. Now, there isn't a single t-score for an alpha error of 5% or 95% confidence interval. The t-score for that is dependent on the sample size, so I would have to look it up on a chart. That would be my critical value of t. Okay, so I'm going to complete this. I'm going to say x bar is 151.4 plus or minus 1.96 times the standard error, which is 7.6. So my margin of error is equal to roughly, looks like about 15 or so. So if I add and subtract that from 151.4, I'm going to wind up, and I'm rounding, grossly rounding here, just to speed things up a bit so we can cover more material. So that's going to be about 135, between 135 and 160 and 165. Right? So we're 95% confident that the true mean cholesterol for the population where this sample was taken from is between 135 and 165. Okay, that's our confidence interval. So, any questions so far? Does that make sense to you? Okay, let's move on then and find one that where we don't know the standard deviation. Well, in fact, we have another one here. Okay, calculate the, okay, where are we here? Repeat the study above. Sample mean was 155. Now this time we're using the sample standard deviation, which is 38. Now this time, instead of making believe that we knew the population standard deviation, we're going to say that the sample standard deviation is 38, not the population standard deviation. So how does that change things? Well, let's go back to our workbook. Okay, and okay, this time, let's see, our mean from our population for our sample is equal to 151 point, what was it again? 4. And our mean standard deviation from our sample is 38, just as before, same numbers. The only thing that's different now is that that's the sample standard deviation. That's not the population standard deviation. So that's an extra element of uncertainty. We're getting it from the sample, not from the population. Our sample size is 25. Okay, so now I'm going to set up the same formula. X bar plus or minus the margin of error, which is equal to, this time, my t-score for alpha is equal to 0.05 times my standard error. Okay, standard error is calculated the same way, except this time we're using standard deviation over the square root of n, or 38 over 5, which is 7.6. Okay, now of course, if you really did the sample, you're unlikely to get exactly the right amount for the population standard deviation. But for our purposes, we want to contrast the difference between knowing it and not knowing it. Okay, the population standard deviation, that is. Okay, so now, instead of using z, now I'm going to set this up 151.4 plus or minus t times the standard error, which is 7.6. The only thing that's different now is what t is equal to. And in order to find out what t is equal to, I have to go to a table. Now, you can also get this from Excel, but Table is just fine. Okay, here's the t-values. Now, it's a sample size of 25. The way we use this table, as we've discussed before, is that the degrees of freedom is equal to the sample size minus 1. So when we look up the values that we're interested in, we're looking up just one less than the sample size. So this is 24. So if I go across here, if I look at the top, a 95% confidence interval, which means an alpha of 5%. Well, let's see, it says right tail probability 2.5%. Why am I getting 2.5% instead of 5% there? Well, that's because it only shows the right tail, the amount of error that you're going to allow yourself on the right side, in other words, overestimating, versus the right and left tail, which would be the left tail would be underestimating, being on the other side of the distribution. So you'd have 2.5% on the left, 2.5% on the right. So you have 5% chance of being wrong at this exact t-score. So I'm going to go down to 25. So it's going to be our middle column here. And 24 is 2.064. So now instead of using 1.96, we're going to use 2.064 to do our calculation. Okay, so thanks for the reminder there on the mean. Okay, so let me get the calculator up. So this time, okay, let's see, 2.064 times 7.6 is equal to 15.68. That's our margin of error. I'm going to put that over there, clear. Now I'm going to subtract that 51.4 minus our margin of error, and it's 135.7. And let's see, 151.4 plus our margin of error. It's going to be 167.0864. Notice how that range is a little bit wider than it was when we knew the population standard deviation and could use Z. And that's because we're not as certain as a result. So when we're not as certain, we have to have a wider confidence interval. Okay, so if we want to be 99% sure, we need a very wide confidence interval. If we want to be 95% sure, we can make a narrower confidence interval. If we're willing to be only 90% sure, we can have a yet narrower confidence interval. So as the level of confidence goes, as your desired level of confidence goes up, you need a wider range of numbers in order to make sure that you actually capture the true population mean between those two numbers. Okay, so let me see what else we got on that. Trying to remember, was there any other problems on this particular homework that were an issue? I don't think there were. Now for proportions, okay, when we work with proportions, we're doing something very similar, except we're using a slightly different way of calculating the proportions, the confidence interval for the proportions. First of all, when we're working with proportions, we typically are going to be working with large samples. So we usually will be using the p-value, the z-value, instead of the t-score for proportions. So in this case, a random sample of 100 zombies, 58 of them were male. We want to know what's a true proportion for the entire population of zombies that are male. So let's say 58 out of 100, that means 58% in this sample of 100 were male. Now notice 58% that were male, that means that 42% were female. You always want to have a sample size on both ends of this, 58 and the 42, that's greater than 15. Okay, you typically want a sample size of at least 100 or 200. So let's give it a try. So 58 out of 100. Okay, so my true proportion, P, my true proportion, P, the percentage of male zombies is unknown, right? We're never going to know a true proportion because we're not going to sample all of them. They're hard to find. Okay, so instead, we're going to calculate a confidence interval, 95% confidence interval in this case. So in order to do that, I'm going to say, okay, so I'm going to emulate my point value for a numerical variable was x bar. My point value for proportion is p cap. P cap plus or minus, that's the proportion that we found in our sample was 0.58, plus or minus our margin of error. Okay, what's our margin of error? Our margin of error is equal to, it's going to be equal to our z-score, which is 1.96, times our standard error. Now, calculate our standard error. We say it's equal to the square root of p times 1 minus p, actually p cap in our case, 1 minus p cap over n sample size. So our standard error is going to be equal to the square root of 0.458 times 0.42 over 100. And take the square root of that. Let's give that a try. Clear my memory. Okay, 0.58 times 0.42 is equal to this, divided by 100 is equal to 0.002. Now I'm going to take the square root of that. Now, with fractions, of course, when you take square root, it's going to become a bigger number. Okay, it's going to be 0.049. I'm going to call that 5% for my purposes. So we're 95% sure that the true proportion of zombies, p cap plus or minus, okay, p cap is 0.58, I'll fill that in there, plus or minus 1.96 times 5%, 0.05. Okay, so this is roughly 2 times 5% is 10%. So our 95% confidence interval is 0.58 plus or minus 10%. Roughly, you could figure this out exactly. Okay, so that's going to be 0.48 to 0.68. Okay, so be honest with you, we're not 100% sure, we're not 95% sure that it's not 50%. Could be 50-50, like this, based on the sample and the sample size that we took. And equals 100. Okay, so in this case, we're 95% certain that the true proportion of male zombies is between 0.48 and 0.68. Questions so far? Okay, these are not hard, right? Confidence interval problems are not hard. Hardest part is knowing when to use T and when to use Z. And for the most part, you can pretty much expect that maybe I'll throw in one kind of giveaway problem where I tell you the standard deviation of the population. But for the most part, you'll be using the T table, okay? Because we'll be working mostly with samples. What was that you were uncertain about? Good question. I don't remember what I was on. I guess the problem asked, what is the true proportion of males in this population, right? And I don't remember. Did I say I was uncertain about something else? At any rate, let me go to Excel and mention that there are a number of functions buried in Excel that we can use to our advantage. For instance, equals tdist, parentheses, and notice that you can put in a value there, right? So I'm not gonna I'm gonna use this on one of the problems later on because you will have some use for this. But there also is t dot inverse. Let's see what that does. Okay, so let me see here. I think when I did that previous problem, was a sample size was 25. I'm going to have to check this, 0.05, comma. I'm going to do this first and then discuss it, just to make sure I remember how this works, whether or not this is two-sided or one-sided. Oh, okay, no, it's okay. So I got it, okay. There is a function. Let me blow this up so you can see it. There's several functions in Excel. T um, 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 uh, T inverse and T dist. Okay, so let's talk about how we might use these. Okay, T inverse. Let's say that you know the probability that you want, but you want to know what t-score represents that probability. Okay, so for instance, if I was working with a problem where, for example, where I needed to go to the chart to look up what the critical value of t was for a 95% confidence interval and for a sample size of 25, as we just did a little while ago. I need the t value, right? Well, the way I would find that is I would click in here, put an equal sign in and say t inverse, parentheses, and now it's asking me for the probability. It's asking me for the p-value, or the percentage of likelihood of being wrong if you reject the null hypothesis. What is that p-value? Well, for a 95% confidence interval, we're willing to accept up to a 5% chance of being wrong. Okay, the only problem here is that this p-value, just like that table, represents only one tail where you could be wrong. The upper tail, for instance, the upper 2.5%. Okay, so in other words, if I want a 95% confidence interval, instead of putting 0.05 in here, I'm going to put in 0.025. I'm going to hit comma, and then I'm going to put in my sample size. Well, actually, not my sample size, my degrees of freedom. Okay, so before it was sample size 25, so I'm going to put in 24, close parentheses. Now, when I hit enter, I'll get the same value that I got, roughly the same value. I think I rounded it to 2.4 before, but I get roughly the same value as I had before. Okay, so now let's use this other function, tdist. Okay, this function, if you calculate a t-score, right, later on in the other problems, you're going to be calculating a t-score. If you calculate a t-score, and now you have to convert that into a p-value, a probability of being wrong, well, let's see what it is for. Let's say that your t-score, notice x, degrees of freedom, and number of tails. This one at least gives you a choice on number of tails. T inverse, only you have to give it the area and one tail. This one, you could tell it that the area you're interested in, you can tell it that it's a two-tailed analysis, okay, which is usually what we're doing. Okay, so the x value, okay, x value is the t-score that you got, 2.39, okay, comma, degrees of freedom, 24, comma, and number of tails, two tail. So the probability of getting this extreme of value, 2.4, when we do a t-test, is the probability that we'd be wrong if we rejected the null hypothesis is going to be about 2.5%. Okay, so that's again, I did a two-tailed test, so it came up with only the part on one end. Okay, so it's a little confusing, right? So sometimes it's a little bit easier just to use the tables rather than to do this. Now we can also, we're also going to be doing some work with SPSS, which will give you the p-value as well. Okay, so at any rate, if I put a one-tailed test, it would have come in 5%, because then it would have been 5% in both, in all at the upper end of the distribution. Okay, but that's a whole nother story. I don't want to get too lost on that. If you really want to use that, that's the way that you would use that. Um, uh, so let me move on to number 5. Okay, number 4, number 5. Okay. Now somebody definitely asked me about question 11 on number 5. Is that correct? Yeah, I think it was. Okay, let's start at the top. Okay, I started to get you dizzy there. You wish to test the number of fouls called in a regular season game is different than during the NCAA tournament. The mean number of fouls caught during all regular season games. We know that mean is 40.1 because we could go back in time and we could actually check every game. Turns out the mean is 40.1 during 16 randomly selected playoff games. In other words, sample size is 16. The mean number of fouls is 38.1, and the standard deviation of the sample, these 16 games that we randomly sampled, was 5.8. So we know X bar and we know standard deviation. We don't know sigma. Calculating 95% confidence interval for the mean number of fouls during the playoff game. Okay, so let's give that a try. Let me get rid of this. Okay. So let's see. If my sample size is 16, my mean is equal to 38.1. My standard deviation is equal to 5.8. And I want a 98% confidence interval, 95% confidence interval. Okay, so my formula, X bar plus or minus. Now, since I only know the sample standard deviation, I'm going to be working with T. And T for alpha is equal to 0.05 times my standard error. Okay, X bar is equal to T. Now, T is going to be equal to, for a sample size of 16, T, let me see if I can't find it here. For a sample size of 16, or 15 degrees of freedom, my T critical is going to be 2.131. Okay, that is going to be the T score, which represents exactly 2.5%. The distance from the center of the distribution to there is 2.5, is 2 point, where am I again? 2.131. 2.131 standard deviations or T scores above the mean and 2.131 standard deviations or T scores below the mean for that sample size. So 2.131 is our critical value of T for that sample size. Let me go back here again. So T is going to be equal to 2.131 times my standard error. My standard error, again, is equal to the standard deviation, since I don't know sigma, or the square root of n. It's going to be equal to 5.8 over 16. Square root of that is 4. So that's going to be equal to 1.18, 1.45, I think. Right? That leaves 18. Go into that. 16, 2 over 4. I think that's right. 1.45. So let's see what we have here. So it's going to be X bar, which is 38.1, plus or minus. Okay, let me calculate this margin of error now. Don't see it. Must be hiding behind something. There it is. Okay. Let me go back here. So 2.131, 2.131. And I'm going to add this times my standard error is 1.45. Okay, that's about 3, and I'm going to save that here. So let's add and subtract that. 38.1 minus my margin of error is 35. plus my margin of error is 41. So roughly 35 to 41. Okay, and the hardest part about this whole thing is basically remembering how to calculate what t-score to use in order to do this. Okay, so now let's get past this idea of confidence intervals. Let's start getting into some tests. Okay, so we're going to use this t-distribution in order to test whether or not one group is the mean of one group is equal to another group, then we have to set up a hypothesis. Okay, so we're going to take a look at this now. Let's start with this question. Let's see. Percent confidence. Okay, let's use this one. The forced expiratory volume for males 20 to 40. That's a pulmonary function test. Many of you guys know that. Okay, is known to be 3 liters. I think that's the amount of air that you can expel in like 1 second or something, per second of blowing out vigorously. You randomly select 63 males. You know that the average for the entire population is 3 liters. That's very well documented. They use these kind of references all the time. Okay, so you want to know if male construction workers in this age range who are subject to a high level of construction dust, if their FEV values, average FEV values for that population is different than for the entire rest of the population. So we're interested in whether one mean for one group is equal to the mean for another group. Okay, so when we write a null hypothesis out, we're always talking about population means. Okay, so we want to know if there's we don't now notice this question doesn't ask is it greater than, is it less than, is it just asks is it different than the general male population at the same age, right? So our null hypothesis is that the mean for all males is equal to the mean for construction workers. Now there's other constructs you could have here. For instance, if you were asking if the mean for construction for all males is greater than construction workers, in other words, your expectation is that they're going to be less, then you might do a single-sided test like this. We're going to stay away from that for now, at least for this test, right? So don't expect that you're going to be doing a single sample test for this test. Okay, this also greater than is also a single-sided test, greater than, less than, and so on. This one, mu for all males does not equal mu for construction workers. Well, that's not a good null hypothesis. That would be an inequality. That would be a good alternative hypothesis. So this is our null hypothesis, and this would be our alternative hypothesis that they're not equal. Okay, so now using the data that we have up there, let's actually go ahead and do this test. Okay, so we're going to do this manually. We didn't get a file. Maybe we did get a file. Hang on a second here. I think maybe we did. Yeah, we did get a file. You know, I'm going to do this a couple of ways because it'll inform us on all the ways that you might do this. Okay, so now I'm going to do this manually first. Okay, so let me copy out all this information that we know about these two groups. So the mean for all is known, and that's equal to 3.0 liters, as it happens to be. Okay, let me go back up here and find the rest of this stuff. We took a sample size of 63, and the mean for that group I didn't give it to you. Too bad. Okay, I didn't give it to you, so you can't do it. You can't do it manually. I didn't give you the standard deviation. So we're going to go ahead and do it in SPSS. Maybe I'll go back after SPSS and do it then. Let me take a look at that question while I'm here. So we use the t critical score, not the t value. In this example, we use the t value you use when you're comparing two things. T critical is what you're generally using as a reference for whether or not you've achieved your goal of rejecting the null hypothesis, or for calculating your confidence interval. Okay, let me close this. Okay, first thing I'm going to do is I'm going to go over here, analyze descriptive statistics, and just get descriptive statistics for this. Just as simple as descriptive statistics for our sample of 63 people. I'm sorry, 60 people. 60 people. Minimum of 1.6, 4.60. The mean was 2.83. It was less than the 3 that we expected represents the total population, and the standard deviation of the sample is 0.52. Okay, so I'm going to go back and I'm going to use those two things. Mean was 2.831. X bar equals 2.831, and standard deviation for my sample was, I forgot it already, was 0.52. So I'm going to take a look at this. I'm going to say to myself, well, gee, my sample size was 60, right? So I need to figure out, gee, what is my standard error here? Well, my standard error, number one. So let me just keep this. This is the population. This is the sample. N is equal to 60. So I want to compare this mean to a known value. That's called a single sample t-test. Okay, most likely on the exam, I won't ask you to do a independent samples t-test where you have to do where you have to actually work with two samples and actually calculate either a pooled or non-pooled standard deviation and so on and so forth. I'm probably just going to ask you to do this manually, maybe for a single sample test. Okay, known mean, we're comparing a mean of a single sample to it. Okay, but you'll have SPSS in order to do those problems that are a little bit more difficult. Okay, so let's see how we would do this. So our standard error, we know our mean of our sample, we know our standard deviation of our sample size. So now I need to know my standard error. So my standard error is going to be equal to my standard deviation over the square root of the sample size, which is 60. That's 0.52 over 60, square root of 60. Let's figure that out. Clear? Clear? So let's see, square root of 60 is this, and 0.52 divided by square root of 60 is that. I'm going to clear that, and I'm going to put this into memory. So that's our standard error. It's sitting in memory right now. Standard error is equal to 0.07. So now I have to determine, is this mean far enough away from this mean in order for me to reject my null hypothesis? And the level of confidence that I want is 95%, or in other words, alpha is equal to 0.05. Okay, so let's take a look at how I would do that. So I need to know if the difference in standard errors in t-scores is big enough. So t is equal to, it's equal to the difference between this mean and this mean. I'm just going to do it this way. Normally I would do x bar minus mu. I'm going to do it this way, just keep the numbers positive. It's not going to make a difference. I'm going to call it 2.83 over my standard error, which is equal to 0.07. Okay, so let's see what that comes out to. That comes out to 1 point, let's see, 0.17 over 0.07, roughly, very roughly. Okay, I'm hoping I didn't round this off so much that's going to change the answer. So 0.17 divided by 0.07 is equal to 2.42. Boy, that's coming up a lot today, isn't it? Is equal to 2.43 actually. Okay, our t-score for our calculation is 2.43. That's how far apart 3.0 and 2.831 are in terms of standard errors. That's the number of t-values, like z-values, that they're apart. Would have been z-values if we had known what the standard deviation of this population was, if we could assume it to be the same. Okay, so how am I going to, let's see, is that big enough for me to reject my null hypothesis? Remember, our null hypothesis was mu1 is equal to mu2, construction workers versus all versus construction workers. And our alternative was mu all does not equal to mu for construction workers. Is this different enough? Are they far enough apart for me to reject the null hypothesis and accept the alternative hypothesis? And it's equal to 63. How come I only got 60 there? The data set that's over there says 60. I guess the problem was a little bit different. I'm not sure that this went along. There might have been another problem that the data set went with, was intended for, something like that. But the data set I have just happens to be 60 for some reason. Okay, maybe I downloaded the wrong one. Who knows? Doesn't matter. Just as long as we're on the same page with how to actually do this. So at any rate, how do I know if that t-score is big enough? What do I compare that t-score to? What's the t-value I have to compare that to? I have to know what t critical is. And what determines what t critical is? What determines what t critical is how much chance of being wrong I want, 5% or 95%, and what my sample size is. I'm going to stick with 60. I know that I might have a little issue here with the sample size. I'm going to stick with 60 for our purposes. So let's get our t table. So what is the critical value of t for a sample size of 60? Well, degrees of freedom would be 59, but we're so far up here that they don't bother with that. They just make jumps to 10. So I'm going to stick with 60. So our t critical for 95%, right, 5% alpha, our t critical is equal to 2.00. It's a little bit bigger than the z-score, but it's such a big sample, so big a sample. That's really close anyway, right? 2.0. So t critical is the t that would give us exactly a 5% chance of being wrong is equal to 2.0. Okay, so have I exceeded t critical? Yes, I have. So what does that mean? That means my probability of being wrong is going to be less than 5%, right? That's what happens when you exceed t critical. When your number is bigger than t critical is for that sample size, that means your chance of being wrong if you reject the null hypothesis is less than 5%. And since my chances of being wrong is less than alpha, less than 5%, I reject the null hypothesis and I accept the alternative hypothesis. I don't know what TP is for sure, but if I do it with SPSS, it will calculate what P is for me. So I'm going to go back to SPSS, and this time I'm going to say analyze, and the function I'm using is compare means, of course. This is a one sample t-test, right? Because we know the mean that we're comparing. We know this is a sample with all this information about the mean of the sample, standard deviation, and we're comparing it to a known value of 3.0, which is the mean for the other population, for the general population. I'm going to click OK. We'll get our output tables and see if we got the same kind of results. Now remember, we did a lot of rounding here. So negative 2.5, they kept it in that same order. I changed it because just play with positive numbers. That looks about right. Degrees of freedom is 0.5. Now our true p-value is 1.5%, which is well under our alpha of 5%. So indeed, we can reject our null hypothesis. And in the case of using SPSS, we even know that the chances of being wrong if we reject our null hypothesis. In other words, getting this extreme of value for the mean from a sample this size, if there's no difference between these two populations, that would only happen 1.5% of the time. It could still happen, but the frequency with which it would happen, the likelihood of it's happening, is low enough that we're willing to just go ahead and reject the null hypothesis. Okay, so I'm afraid you got to be more specific when you say I've been doing a lot of talking here. When you say repeat that one more time, I'm not sure which part. Do we mean the this part about that this is a one sample t-test? Exactly right, because we know we only have one sample. Now we're going to move on to 5B, and in 5B we're going to be looking at situations where we have more than one sample. How did you determine that it's lower than 0.05? Anytime your t-test exceeds the critical value of t, the critical value of t for that sample size, anytime you t, that means that your p-value is always going to be less than 0.05. That's why it's called the critical value of t. Okay, and SPSS actually calculates that p-value for us. It's likely you'll have at least one of these problems you'll have to calculate by hand. You'll have some multiple choice. You'll have some some short answer questions. You'll have some short problems. Might ask very similar to kind of like the homework, except I probably if we go to 5B, I gave you some pretty difficult calculations to do. For calculating pooled standard deviations and so on and so forth. I may have a little bit on that, but I hope not to get too complicated with that. Okay, so you'll get a little bit of that, but the harder stuff, the more complex stuff, will be stuff that you'll use SPSS for. Oh, one-tailed test. You want to know something, Mike? I would love to talk about one-tailed tests now. Yeah, 5B is much more challenging. I want to go to that now. And in fact, I'm thinking that on Tuesday after Monday's class, we're gonna be going over some of this. We're gonna go to analysis of variance, but we're also gonna go over a bit of this again. And I think we'll concentrate on on looking at some of the problems in 5B before we move on to analysis of variance and start discussing that. Okay, yeah, 5B was pretty challenging. I have to admit that because it required you to do a lot of the front work of actually doing the calculations, not so much relying on SPSS. There'll be some stuff from 5B, but I'm not going to get crazy. Okay, let's tell you what. Let's see how things go on Monday night, and we'll see how much of this stuff we can get through. And I'll give you some clarifications on that, like what you can expect in terms of what kind of problems you should be able to do. Okay, so where are we now? Let's see. We're pretty late on here. Let me go to 5B now. Let me just go take a quick look at 5B with you guys. Okay, so 5B, we start to get into this idea of of multiple different kinds of situations that we could be in when we're working with two samples. When we're working with two samples, gee, we could have two samples with equal variances. We could have two samples with unequal variances, or we could have paired samples. Paired samples are really kind of the easiest of all of these. Okay, and I think there's one of these that involves paired samples here. Let's see if I have. I don't think I have I don't think I have data available right now for paired samples. But when we're dealing with two sample t-tests, there was a form that I gave you guys, a document that outlined. Let me see if I have it here. There it is. So there was an outline that I gave you guys. Nope. Don't want that now. This basically summarizes the formulas you would use for when you're comparing two samples, depending on whether or not they have equal variances or unequal variances. Okay, so there's two possibilities here. You could have two samples and they could have equal variances, equal standard deviations. Or you could have two samples and they could have unequal standard deviations. If they have equal standard deviations. Now, for our purposes, you need me to look at 5B? I got the value for 11 kilos. I'm going to do 5B right now. Has anyone got the answer to 5B? I use the values from the answers before, which I got correct, but the value for 11 comes up as wrong on 5B. Let me just get through this, and I'm gonna hang around for a few more minutes past 9 here, and we'll see what we can do on question 11. Okay, but I just want to get through this now. For our purposes, when we're calculating manually, and I'm hoping you won't be doing too much of this, maybe a little teeny tiny bit. When calculating manually, based on whether or not the standard deviation of one sample is twice the other, is how we decide whether we're going to assume them to be equal or not. That's kind of a loose rule. Okay, so if the standard deviation of one is 10 and the other is 8, we're going to assume that they have equal standard deviations. If that's true, then we're going to use this formula to get a weighted average of the two standard deviations. Standard deviation pooled is equal to the two standard deviations squared times the sample size minus 1 of each one. Just work that out and you get a pooled standard deviation. And then, in order to calculate my t-score for the two samples, it's the difference between the two means, the distance between the two means over the standard error. And the standard error is going to be the pooled standard deviation times the square root of 1 over n1 plus 1 over n2. So a little complicated, but I mean, if you're careful with your math, this shouldn't be a problem. You get a t-score. Your degrees of freedom are the sum of the two sample sizes minus 2. So you go to your t-table, you get your critical value of t, which is, if it's sample of size 9 and size 9, that's 18 minus 2 is 16. So you get your t-score for 95% confidence interval for sample size of 16, which is 15 degrees of freedom. And that's your critical value of t. And then you compare it to the t you calculate to see if your t is greater than the critical value. And this is your standard error, and this is the difference between the two of them, two means of the two samples. So once you calculate your t-score, you can compare it and decide whether to reject your null hypothesis. If they're more than twice the other, then you assume that they're not equal. Standard deviation more than twice the other. You assume that they're not equal. So you wind up with this formula for your t, where you got x1 minus x bar 1 minus x bar 2, just as you had always on the top, and this represents your standard error on the bottom. In fact, it's a little easier to calculate than it was before. Okay. Now the only problem is now you have to calculate your degrees of freedom, and the degrees of freedom is a rather complicated formula. So for our purposes, just take the smaller sample size and use that to calculate your degrees of freedom, rather than go through this torture with this formula. Okay, that would be probably good enough for our purposes. Okay, and again, you look up your critical value of t, which is based on your degrees of freedom, which is going to be, for your purposes, the smaller sample size minus 1, right? And you're going to compare the t you calculate by taking your difference in the means over your standard error. You're going to take that, compare it to your t critical. If it's greater than your t critical, you're going to reject your null hypothesis. So let's go back, and that was question number 11 on 5B. Okay, let's go down there. Might have to take a little extra look at this. I am on 5B, right? Is this 5B? Yeah, this is 5B. Question number 11. Calculate t-value for the difference between the two means. Okay, so let me back up here. Here we go. Study was conducted to determine if expected mothers of cigarettes. A sample of 77 newborns whose mothers smoked, and sample of 161 newborns whose mothers didn't smoke. Okay, let me get this out of the way here for a second. I'll move that over there. I need this so I can write down all my stuff. I don't have to go back to that. Okay, so see, let's take our two samples here. Okay, I have two samples here, mothers who smoked and mothers who did not smoke. Okay, so mothers who smoked, I have 77. My sample size is 77. Okay, mothers who did not smoke, my sample size is 161. Okay, so my X bar for mothers who smoke versus X bar for mothers who smoke, non-smokers. Okay, that was, let's see, 0.099. And for mothers who didn't smoke was 0.091. Assume that the variances of the underlying problem, it tells you to assume that they're equal, right? Okay, so let's see, do I have a standard deviation? Standard deviation is equal, okay, which is equal to 0.26 and 0.25. And they're close enough that we're going to assume that they're equal because one is not double the other. Okay, so now what's my t-score going to be equal to? My t-score is going to be equal to, going to be x bar 1 minus x bar 2, which is going to be 0.099 minus 0.091 over my standard error. Okay, now it's going to be a complicated part, right? Because if I go back to our formula there, since they're equal, I have to get a weighted standard deviation. So let me see if I can't get the formula out here. I can't keep that up there and look at it. Oops, I got the wrong page there. Okay, there's my pooled standard deviation. So my pooled standard deviation is equal to the square root of 170, is that 177 or 77? That's 76 times, am I right about that? That's 76 times 0.026 squared plus 160 times 0.025 or 0.25 squared. It must be 0.025, right? 0.025. Right, those two standard deviations? Yeah, 0.025. Oops. It had to be. Let me get this back again. Okay, over the sum of these two samples sizes, which is 77 and 161. That's 238. 238 minus 2 is 236. Okay, anybody anybody see me do anything wrong here so far? 236 is right? 71 and 161 is 238 plus 236. Okay, let me calculate that. In order to do this, I feel more comfortable with Excel because I think I can do it a little bit quicker. Okay. Okay, so this top part, first note is going to be equal to 76 times 0.026 times 0.026. Good. And the second part is going to be 160 times 0.025 times 0.025. Okay, whoops, I forgot to put the equal sign in front of there. Good. Okay, so, and then I got that over 236. Okay, so it's going to be equal to the square root. This is my of pooled standard deviation is going to be equal to the square root of, I'm going to add these two together in my head, 0.151376. Everybody happy with that so far? Actually, I don't want to assume that. Equals a sum. In case the formatting is such that I lose the, yeah, okay. No, it wasn't. Okay, I was safe doing that. Square root, parentheses, of the denominator, numerator over the denominator. Okay, so that's my square root of, that's my pooled standard deviation. Now my standard error, let me get my sheet back up here. My standard error is going to be pooled standard deviation of square root of 1 over 77 plus 1 over 160. Okay, so let's go back to Excel again. Where is it? There it is. Nope, that's not it. My Excel spreadsheet. Okay, so equals 1 over 77 equals 1 over 160. Okay, so let's see. Square root of those two equals square root of some of those two numbers. Oops. Yes. Ah. Let's see if this works. Okay, so this is my standard error is going to be equal to the pooled standard deviation, right? Pooled standard deviation times this value here. Okay, so it's going to be equal to this times this. So that's my standard error. Okay, so now I want to find the difference between how many standard errors apart these two means are. Okay, so what were my means? My means were equal to 0.99 minus 0.091, right? And that's all going to be divided by my standard error. Okay, I got to put this in parentheses first. So my t-score should be 2.27. So does that agree with what is that what the issue is? Is that right or wrong? Standard error is equal to 0.034. Did I get that wrong? Did I do something wrong there? Or is it you saying that that's what the 1 over 160, 1 over 161. Okay, actually, if I'm lucky, one of the nice things about Excel is I can go back in here and fix this. Okay, how's that? Oh, no, still didn't come out right, did it? The 1 over 161. Did I get this one right? 1 over 77. Well, I'll go ahead and check it. Now, what was the problem? The problem was, which problem was it? Was question 11, which asks for calculate the t-value for the difference between the two means. Okay, and the value I got was roughly 2.28. Is that the value that you guys got also? Okay, so that's right. That's the pooled standard deviation, and this is the square root of these two, and this is the standard error. Okay, so this is the t-value that I got. So somebody mentioned that they weren't able to get the same answer, that they thought that was wrong. Is that different? B10, is that correct? Not sure what that is. Oh, 10, question 9, number. I can't read question 10. Calculate the standard error. Oh, in Excel. Okay, sorry, thank you. B10, that's the square root of D7, right, over B8. Oh, no, you're right. Yeah, B8. That's this plus this, right? This was our it's 161. There we go. Hang on a second. Oh, no, that was n minus 1. Yeah, it's 160. That's right. And this should be 76. And this is 236, the sum of the two of them. Okay. So this is my pooled standard deviation. Oops, excuse me. This is the sum of my two. This is the let's see. I got myself confused now. I shouldn't have stopped when I was in a row. Does I got the correct standard deviation pool, correct standard error, but when plugging its standard error to the T formula, I got 2.35, which Blackboard shows is wrong. Let me just read that. I got the correct standard deviation pool and correct standard error. So you agree with me on the standard error, but when plugging in standard error in the T formula, got 2.35 instead of this. So in other words, you got the same value, D10, you got 0.0035. I wonder, did you round this? Maybe that's what the problem was. Is it a rounding error? Oh, but you got 0.034. I wonder if that makes enough of a difference. And you got 0.0034. Yeah, I'm not sure why I got 0.0035. All right, let me take another look at this. 76 times this squared, okay, plus 160 times 0.025 times 0.0 is this. Add the two of them together, I get that. Okay, so divided by 236. So I want that divided by 236. Hang on a second here. There is the top of my formula. There's the bottom. Oh, hang on a second here. Let's see. That's the top is equal to, this is the sum divided by this. And I want to take the square root of that. No, I think I got that wrong. Hang on a second here. This is n minus 1 times standard deviation squared. And this is n minus 1 times standard deviation squared. And this is my n plus n minus 2. Okay, is this. So I want the sum of these two, which is this, divided by that, then I want to take the square root of it, equals sum of these two, right, is equal to the square root, come on, of this divided by this. So my standard error, oh, that's just that formula. Now I got to multiply that by my pooled standard deviation. Okay, where was my pooled standard deviation? My pooled standard deviation, let's see, where did that go? Oh, that is my pooled standard deviation, excuse me. That's my pooled standard deviation. Now I have to multiply, I still got the same answer. Now I have to multiply that by the sum of the inverse of the two sample sizes. All right there. Right. that plus that times pool standard deviation, square root of pool standard deviation. So this is 1 over 77. This is 1 over 61. This should be the sum of the two of them, F7, G7, and find the square root of it. So this times this gives me my standard error. That's my standard error is right. And this is 0.099 minus 0.08 over my standard error. I think this is right. I think I got 0.035. I'm not sure why you guys got the 0.034. Maybe it's a rounding issue. I mean, with Excel, I'm not doing any rounding. April, did you use Excel? April, guys, did you use Excel, April and Vicky, or did you use calculator? Are you doing it out with a calculator? Okay. It might be a rounding issue. Yeah, because Excel, even though you might have noticed there for a moment I froze here, and I said, I was just going to add these two together in my head to get this number. I think it's possible. I got worried that maybe that's a rounding error because in Excel you can hide the extra decimal places, right? If I format that this way, it shows the extra decimal places. I was worried that that was formatted only for a single decimal place, and I wasn't seeing the rest of it. So I actually added it using Excel instead, so I wouldn't do that. So even when you only show like a fewer decimal places in the formatting, it still uses the highest precision that it has for the actual calculation. So I'm thinking maybe that it's a rounding issue. And I think that if it's that close, I need to make the acceptable range wider in SPSS. Okay, so now our t-score was 2.279 or 2.3. Okay, let's go with that 2.3 or 2.27 for the moment. Let's April and Lincoln both got 2.35. Okay, I think it's a rounding issue because I'm not sure you're carrying over all the decimal places that you might, because I mean, for instance, like that something like this, I'm not sure you would be typing in every one of those digits, and in fact, there's actually maybe even more than that, right? Could be even a bigger number. So I think that might be a rounding issue, but I'll take care of that. Now let's get back to the point though. The point is can I reject my null hypothesis? This is the t-value that I calculated, correct? That's the t-value that I calculated. What's my t-critical for this problem? Okay, if you go back to the sheet there, how do you calculate? Yeah, t-critical is going to be, we're going to add up the two for equal standard deviations. We're going to take the sum of the two sample sizes, the 77 and the 262. What was it again? 77 and the where is it? 161 adds up to 238. We're going to subtract one from it, so our degrees of freedom is 236. Okay, so 236, if I go to my t-table, my z-score for 236 is my t-critical. Because it's such a big sample size, my t-critical is almost going to be 1.96, the same as z, just because it's such a large sample. Let's call it 1.97, just to be fair, right? So is your t that you calculated bigger than t-critical? Yes, it is. So what can you do with your null hypothesis? Yeah, we reject our null hypothesis and we accept our alternative hypothesis. Okay, so that's how we would deal with that. You know what I'm going to do? I will do this on paper, step by step, and show you every number and how I got to it. And I'm also going to go back and make the range wider because I think what happened is that when I did it, I almost always use Excel for this kind of stuff. So it's just so I could go back and check myself or make corrections if I make an error very easily. So what I'll do is, and I got a feeling you would never type this into a calculator. I mean, it's just too much. I think it would be a rounding issue. So I'll make sure on the test and on this homework that I make the range on this problem wide enough that it covers that. But I'll also post a more detailed version of this with it worked out. Okay, and again, we'll get a chance to go over this again tomorrow night. So good night, guys. Let's call it a night. And I'm sorry that we have such a short summer semester, and I have to make you guys interrupt your weekends and stuff like that to get a little extra in. Okay, bye. See you tomorrow.